Hello, students. Welcome to week 5. Today we're going to be covering chapters 5 of the textbook. And before I start, I'll just probably take a couple of minutes just to just be clear as to the intent of this video. The intent of this video is not to replace the inline class. The intent of this video is really just to kind of talk through the chapter. Maybe highlight some areas that may pose some difficulty for you guys to double click on those. I'll try to explain what I can, but again, the intent of this remote course is for you folks to explore the vast resources that we have on the web to do some further investigation and further reading on some of the subject material. I will find some videos that I think are helpful again, but it's up to you guys to find some of those videos that can help yourself, that would help you. And again, if you're reading a very specific section of the textbook and have a very specific question, feel free to reach out to your colleagues, reach out to your classmates, or send me an email and I'll be able to respond when I can. Okay, so with that out of the way, let's get started. So this is week 5 of the course, and we're going to be covering instruction sets on computers, how computers execute instructions. In chapter 4, we learned about the Mary computer. You learned about some basic instruction sets of the Mary computer. And in chapter 3, going back, we learned about Boolean algebra and how information is represented in computers, digital logic. And in chapter 2, so all of this is coming together, right? Instruction sets is how computers actually execute instructions. So the objective of this week is for us to kind of understand the factors involved in instruction set architecture. In later sections of the textbook, you would see this abbreviated as ISA, instruction set architecture. But again, it's just a bunch of instructions that the computer executes when it's doing a job. Okay, and we're going to gain familiarity with what we call memory addressing. Data is stored in memory in the computer, how the computer addresses the memory. And we're going to understand the concepts of instruction level pipelining and its effect upon execution performance. Pipelining is just the mechanism that computers use to execute many instructions at the same time. Pipelining. Okay, so like I said, this chapter builds upon ideas in chapter 4. We talked about the Mary computer in chapter 4, a very simple computer. Mary stands for, God, I cannot remember, but it's a very simple computer. You learned about instruction sets from there, and you saw some assembly language instructions of the Mary computer, okay? So in this chapter, we're going to be looking at instruction sets, different types of instruction formats, operand types, memory, how memory is accessed, and we'll see an interrelation between machine organization and instruction formats. And I think at the end of this chapter, you have a better understanding as to how computers execute instructions. Now, there's a key word that I like to just call out so that we don't forget. And that key word is, let me just open a notebook here so we can be collecting those as we go. That key word is, so let me just do chapter 5 notes. Okay. So some keywords. That keyword, one of the keywords is what the textbook calls it, an opcode. An opcode is the instruction that the computer is executing. Okay, so we have to be very clear with this term. These terms are going to come up over and over again in this chapter. Oops, not that. And an operand, which is what the textbook calls, and this is on page 299, by the way. An operand is an operand specifies the register or the memory location of data. Okay, operand is the register, is equal to register, equal to register or memory location of data. Okay, so just pay attention to these two keywords. Opcode is the instruction that the computer is executing, and operand is the data. Okay, let's make a note of this. Okay, so now back to the slide deck. So instruction sets are differentiated by the following: the number of bits per instruction. And by the way, folks, an instruction comprises of an opcode, one or more opcodes, but generally let's say an opcode, and operands. Okay, there could be one or more of either of these, but the collection of both an opcode and an operand give you the instruction. Okay, that's an instruction. Okay, all right. So the number of bits per instruction, and whether the instruction is stack based or register based, we're going to talk about that. Excuse me. The number of explicit operands. Remember, operand is, what is it again? The data blocks that the instruction contains, and the operand location, the type of operations, and the type and size of operands. Okay, remember, operand is going to be the data. Like I said, pay attention to these two keywords because these words will be coming up over and over again, and this is on page 299 of your textbook. All right? Okay. Now, let's keep moving forward. Let's see what the next slide says here. So we're still going about instruction formats. Instructions and architectures are measured according to the main memory space occupied by the program. Instruction complexity, again, remember instruction is the operand and the opcode. Instruction length, how many bits is used to store each instruction, and the total number of instructions in the instruction set. Remember, instruction set architecture is ISA, is the number of instructions, or all the set of instructions that this computer supports. In chapter 4, you saw the memory computer, right? It supports a limited set of instruction sets, right? So the number of instructions in the instruction set also is what differs one architecture from another. You'll see towards the end of this chapter that Intel, for example, the Intel architecture has a different instruction set from RISC and from ARM. Okay, so that's what this means. All right. So when designing an instruction set, several considerations are taken, right? One is the instruction length. How long is the instruction? Remember, instruction again is the opcode and the operand. So how long should that instruction be? The number of operands. So how many data blocks? Remember, operand is data. How many of data blocks are in an instruction? The number of addressable registers. A register is one of those memory blocks in the computer, which I think you learned in chapter 4. Memory organization, whether we're addressing memory by byte or words. A byte is 8 bits, a word is 16 bits. And addressing modes, which we'll talk about in later sections. Okay, so again, just speeding through this so that we don't have this video a little bit too long. Now, byte ordering. So in page 201 of your textbook, you'll read about the word endian. I don't know if that's how you pronounce it, but it's just the byte order. Byte order. So a byte is 8 bits. Okay. If you want to represent an information using 2 bytes, let's say you want to represent an integer using 2 bytes. And do you put there's something called the low significant byte and the high significant byte. So the position of the low significant byte with respect to the most significant byte is what determines the endianness. So if I try to draw a box here, let me see if I can draw a box real quick. Or let's put a table. If I put a table in here. Okay, so if this is the low significant byte and this is the most significant byte, this is called little endian. Okay, let me just confirm that. Okay, little endian is, let's see, let me confirm that. Little endian, some machines store 2 bytes, the least significant byte, yes. Okay, so this is little endian. Just wanted to confirm that. So I'm not giving you guys wrong information. And then if you reverse the order where you have the most significant byte appearing first in this. Remember, this is a byte, so this is 8 bits. If this is the most significant byte and this is the least significant byte, this particular one is called, if that's little Indian, this is big Indian, okay? And big Indian is represented by Unix machines. Unix machines use big Indian, while Windows machines, from what the textbook is saying and for what I remember reading this earlier, Windows machines, PCs, most Unix machines are big Indians, whereas most PCs are little Indians, right? So this is PC. So read about this. And again, it's just the order in which the bytes, the least significant byte and the most significant byte appears in a 16-bit word. Okay? So I hope that is a little bit clear. Again, relatively straightforward. If you have any questions, please feel free to reach out. So how does Indianness impact? Let me just move my face here a little bit. Let me see if I can reduce this. Okay, let's put it there. So how does Indianness impact the memory address? So this is there. So here's what I was talking about, right? In Big Indian, the most significant byte is represented in this in the left side, right? And in Little Indian, the least significant byte is represented here. So as an example, suppose we have the hexadecimal number OX1234567. This is hexadecimal. Okay, so this is going to be exactly represented like this in memory. So in Big Indian, let's start with Little Indian. In Little Indian, this is the least significant byte. 8. 78 is the least significant. 56 is again the least significant, but it goes from right to left, right? Again, this is the least significant byte and this is the most significant byte. So you see in Little Indian, 78 is represented here, 56, 34, and then in Big Indian, the most significant byte is represented first, and so on and so forth. Okay, so again, just pay attention to that, and relatively straightforward. So just additional examples here. We don't have to go through this, but you can just look through these examples, and if you have any questions, please feel free to do further research or reach out. Now, there's obviously a difference, right? There's a difference between the Big Indian and the Little Indian. As you guys saw, I was tripping over trying to read the Little Indian versus the Big Indian because the Big Indian is a little more natural, right? If you translate this into memory, it's very, very natural in how we read those numbers. Whereas in the Little Indian, it's flipped, you know? So there's advantages and disadvantages with these mechanisms. Each has an advantage and a disadvantage. For example, you see that this one is more natural to read. The sign of the number can be determined by looking at the byte at address offset 0, and so on and so forth. But again, this is covered in your textbook, right? This is covered in the textbook. I think page 303 really talks about the differences and some of the trade-offs. If a computer architecture uses Big Indian or Little Indian to represent information, there's some trade-offs that are made, and that is kind of covered in page 303 of your textbook. All right. Now, we talked about instruction formats. We'll continue talking about instruction formats. What we're going to talk about now is just consideration for how the CPU will store data. Right? We talked about Big Indian, Little Indian, and now how does the CPU store this data that it has to operate upon, right? We talked about the opcode and we talked about the operand, right? And the instructions. How does the CPU store this data to operate upon that? There's 3 choices. There's the stack. You all are computer science students. You've probably heard of the stack. A data structure is one of the very important data structures in computer science. A stack is used, an accumulator is used, and general purpose register is used This one is what is mostly used in computers today, general purpose registers. A stack has limitations because you have to pop and post. You have to put and pop in a stack. Accumulator architecture has limitations as well. This one is the most flexible, but again, each of them has trade-offs. Trade-offs in terms of their usage. Okay, so I'll just skip this one, but it talks about the stack architecture, which I really just quickly talk about it. I talked about that. Operations, instructions, and operands are implicitly taken from the stack, right? You know, the stack is you pop in and pop out, first in, first out. So you cannot just access items randomly in the stack. You have to pop out the thing that was lastly popped in, you know. So that's one of the limitations of using stack architecture. It's very limited in the way that you can address data. And then the other one is the accumulator architecture. You can only have one operand of a binary operator. Is implicitly on the accumulator. One operand is in memory. So again, read through this, but there's trade-offs. If you're using a stack, which is first in, first out, if you're using an accumulator, or if you're using a bunch of general purpose registers to store data, there are trade-offs with each of these different ways to store data in the computer. Okay, so I'll be right back. Hang on, just one moment. I'll be right back, please. All right, I'm back. Sorry about that. Okay, so we were talking about instruction formats, how information is stored, you know, the kind of storage that is used by the computer to manage the instructions that it has to execute upon. We talked about the stack, accumulator, and general purpose registers. Again, this is covered on page 304 of your textbook. Okay, so read through that, and it should be relatively straightforward reading. If not, like I said, there's a lot of resources online that you guys can use to get clarity, or you can always reach out to me for a very specific question on something that you may not understand. I'll be able to help you understand that. All right, let's keep moving down a little bit here. So, like I mentioned, most systems today use this general purpose registers. Why? Because it's flexible, and a general purpose register really is just a bunch of registers that are there for the computer to use to store operands. Really, right? They can store any kind of operands in there, and you would see later that the computer uses addressing modes, different addressing modes to kind of know how to grab that information from those registers. But it's very flexible. You can store anything on there, which is why a lot of computers today use general purpose registers. So there are three types of general purpose registers. Memory, where 2 or 3 operands may be in memory. Remember, an operand is the data. Again, if you go back to page 299, the operand, right? Operands specify register or memory location of data, while opcode specifies the operation to be executed. Okay, so remember this word is going to be appearing over and over again, so we have to be very clear as to what it is. Operand is specifies a register or memory location of the data. So in a memory type of GPR system, you have 2 or 3 operands, maybe in memory. In the register memory, you would have at least one, could be in a register, the rest in memory. And then in the load store is where you have where no operands may be in memory. There is no operand in memory. I think we're going to see some examples on this in subsequent slides. Okay, the number of operands and the number of available registers has a direct effect on the instruction length. Remember, an instruction is a combination of the opcode and the operands. Right, so now we talked about stack machines. You know, the stack machines will be those type of machines that use a stack instead of a general purpose register. They use 1 and 0 operand instructions. So this would be instructions such as load. If you remember in chapter 4, you saw those load and store instructions. These instructions typically have just one operand. So for example, you would see an instruction such as load X, store Y, right? Load X is loading. This is the opcode, and this is the operand, right? This is the opcode, and this is the operand, right? So you see, this is an instruction. This whole thing is an instruction that has just one operand. Okay, so in this case, this one's gonna be stored in a stack because they have just one operand each. Push and pop, again, are instructions, but these ones don't really contain operands, right? Because when you push, let's see, involve only the stack's top element. Yes, when you push into a stack or you pop from a stack, there's an implicit assumption that when you pop, you're popping off the top of the stack. And when you push, you're pushing to the stack. Okay, and then if you use a stack to store your instructions, you imagine stacks, you're storing information on a stack, you cannot address things randomly. You know, if you want to do an operation with data that's on the stack, let's say that you wanted to execute a multiplication on the stack. So multiplication, let's say multiply X by Y, right? The only way, if this entire instruction is on the stack, the only way that this instruction can be executed is if, you know, the opcode and these two operands are located very, very close to the stack. So if this is popped off the stack, the next thing that's popped is this one, X, and then the next thing that's popped is this one, then the machine can execute the instructions. Right, but for a stack to be used, the instructions, the opcode has to be very close to the operands. So that's what our slide deck is saying here, right? Binary instructions use the top two items on the stack, okay, as the operand. Okay. So read through this. I will leave you guys read through this one. If you have any questions, please reach out. It just talks about how, if you wanted to do an operation using the stack architecture, how the information will be structured. If you wanted to do z equal to x plus y using a stack architecture, how should this information be structured to fit on the stack? So when the machine is executing, it's popping things off the stack and it's executing them. You know, so that's some of the things this is covered in pages 306 of your textbook. Okay, read through that. Again, it's straightforward, and if you don't understand it, let me know. Okay, so there's this ideas of postfix, prefix, infix, prefix, and postfix. That's how the instructions can be organized using the stack architecture for the computer to execute upon that. Okay. This slide is just talking about if you wanted to execute something more complex, how do you kind of simplify this? And we saw some similar algebraic manipulations in prior chapters where there was those rules that you use to simplify algebraic expressions, right? You can also use some of that to kind of determine how a stack architecture can be used to execute complex Boolean, complex mathematics. Okay. I'll leave you all with this one, but again, to work through this example, this is the infix expression. You want to do 2 plus 3. Again, infix is covered on page 306. Then, what is it? Convert the infix expression 2 plus 3 minus 6 over 3 to postfix. You know, so the sum 2 plus 3 in parentheses takes precedence, and we replace that with this. Okay, remember this is the postfix operation covered on page 306. And I think in the next one, the division takes the next precedence. We replace 6 divided by 3 like this. And then the quotient is subtracted from the sum. Right, so we move the operator to the end, and you end up having something 2 plus 3 plus 6 divided by 3. That is the opcode. These are the operands. That is the opcode again between those two expressions, and you get something like this. So okay, again, so this is if you're using a stack, you can go to this example. Unfortunately, I've not been able to find a good tool to be able to give some illustrative videos, but I continue to look for one of those, and if I can find one of those, I will be using those in subsequent videos. But until then, I just have to demonstrate using the slide deck. All right, so this, and I'll make the slide deck available as well for you folks to be able to read through them. So let's skip through this example real quick. And what is this one here? Let's see how to evaluate an infix expression. So with a 3 address instruction set architecture, such as mainframes, this infix which says z is equal to x times y plus w times x. Remember, multiplication takes precedence over addition. If you guys studied BODMAS, I think I studied BODMAS, which said, let me just type BODMAS, which is brackets. What is O for? Something. I think D is division. I think M is multiplication. I think A is addition. And then subtraction. All right, so it goes in this order. So brackets come first and so on and so forth. Okay, multiplication comes before addition. So if you go back to the previous example, you see that x multiplied by y comes first. W multiplied by u comes next. You do this first, you do this next, and then you add them together, right? So if you see that this is multiple, so this would look like this. Result 1 is going to be a multiplication of x times y. Result 2 is going to be a multiplication of w times x. And then you add result 1 and result 2 and you store the instructions. You store the result in z, right? So if you follow this, so this is in a 3 with a 3 address architecture, instruction set architecture. R1 is address 1, X is address 2, Y is address 3. If you use a 2 address architecture, which you can only have 2 operands in the instruction set, right? This is what it's going to look like. So as you notice, there's many more instructions if you use less number of operands. In this case, where we had 1, 2, 3 addresses, we have 1, 2, 3 instructions. In this particular case, where we have just 2 addresses, we have 1, 2, 3, 4, 5, 6 instructions, right? So the lower the number of addresses that you use to store the operands, the longer the program is. Okay? So those are some of the things that we should be paying attention to. So if you were just think about we could only use 1 address. You can imagine this program would become too long because you have to take X, you have to load X, you have to load Y. Then you have to, let's see what a 1 address looks like. You got to load X, yes. You got to actually load X, multiply that with Y. There's an implicit assumption that you're multiplying this Y with X. You're going to store the result in a place called temp. Then you're going to load W, multiply that with U, and then you're going to add it to temp. Again, there's an implicit assumption that you're adding the result of these two to temp, and then you store the result in Z, right? So as you can see, that's what the Mary computer looks like. Okay? So the greater the number of addresses or operands that we can use in an instruction set, the shorter the program, the shorter the computer program. The lower the number of operands that we can use in the instruction set architecture, the longer the program. Okay, so that's really what we're learning here, and I think this is covered in pages There's many examples of this postfix and infix on pages 308 and 309 of your textbook. Okay, so let's see, what's this? I think this is an additional example of using a one operand, using the stack architecture, where you're trying to execute this particular formula, x times y. What is this one? X times y. Yes, again, so we're doing x times y using the postfix expression. And then you do w times u, and then you add these two together. A little bit confusing, but that's what it is all about. Okay. All right. So we've seen operands, we've seen opcodes, and we know that an instruction is the combination of the opcode and the operand. We have seen that some instructions can contain one operand, some instructions can contain two operands, some instructions can contain three operands. And you can just imagine that the larger the number of operands you have an instruction, the wider or the longer the instruction set will be. Okay? So that's what this slide is saying, that instruction length is affected by the number of operands supported by the instruction set architecture. In any instruction set, not all instructions require the same number of operands. As you imagine, a load instruction requires just typically one operand. A multiplication instruction requires two operands. So not all instructions have the same number of operands. And, I think this is what this slide deck is talking about. Now, we start talking about the instruction set, right? So you typically hear of 16-bit machines, or 32-bit machines, or 64-bit machines. It just means that each instruction of the machine is stored in this number of bits. In a 16-bit machine, each instruction is stored in 16 bits. Right? A system has 16 registers and 4K of memory. We need 4 bits to access one of the registers. We also need 12 bits for memory address. So look at this example right here. There's 1, 2, 3, 4. There's 16 bits here. If this is representing a 16-bit architecture, right? And this would represent one instruction. So an instruction will be stored in all the 16 bits. Remember, an instruction is a combination of opcodes, which is the instruction that needs to be executed, and operands, which is the data that comes to the opcode. So if you have a 16-bit machine, you're saying that each instruction is stored on 16 bits. Therefore, the opcode is going to be used, it's going to be used using the first 4 bits, and then the remaining 3 bytes, the remaining 3 sets of 4 bits, I think we'll call them nibbles, are used to store the different operands used for the instruction set. Does that kind of make sense? Okay, so let's keep going down and see what the other slides say. Okay, so if we allow the length of the opcode to vary, now remember the opcode is the instruction. Okay, opcode is the instruction like multiply or add or divide. That's the opcode. If we allow the length of the opcode to vary, we could create a very rich instruction set. Imagine if you have a very fixed number of bits for the opcode, you can only define so many, right? Because again, the number of opcodes must be defined only using 4 bits for example, in this diagram. But if you said no, we want to be able to represent any number, represent opcodes using any number of bits, then you can have a very rich instruction set. So that's what the slide deck is saying, right? So if you look at this one, what is this saying here? 15.3 address codes. I don't understand what the slide deck is saying, so let's skip this one. So given 8-bit instructions, is it possible to allow the following to be encoded? Let's see. So these slide decks are just trying to determine, given the number of bits. So let's say you have an 8-bit architecture, a 16-bit architecture, a 32-bit architecture. How many instructions can you encode using X number of bits, right? So here's an example. Given 8 bits instructions, right? Remember, instruction is opcode and operand. Is it possible to allow the following to be encoded? 3 instructions with 2-bit operands, 2 instructions with 1 4-bit operand, and 4 instructions with 1 3-bit operand. So let's think about this for a second. 2 3-bit operands will look like something like this. Let me just do this real quick. This video is going to be long, but you folks have to bear with me. So if we do, let me just insert a table here. And I am going to give 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's add one more insert column to the right. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So imagine this is an 8-bit architecture. We have 8 bits. Each of these blocks represents a bit. Okay? So what we're saying here is that, is it possible to allow the following to be encoded? 3 instructions with 2 3-bit operands. So we want 2 3-bit operands. So this is, let's talk about an operand. So this is operand, sorry about that, operand. What happened to my internet? Hang on. Oh, what happened to my internet here? Google is trying to connect. I just lost internet connectivity. I don't know what happened there. Hang on, folks. Come on, Google. What happened? Huh? Okay. We're back, it looks like. All right, so let's do this. This is an 8-bit architecture. Okay, 1, 2, 3, 4, 5, 6, 7, 8. This is representing an instruction. So these 3 bits right here, this, I'm going to make color coding here. This 3 would represent, let's say, let's use this color. I want to fill of the cell. How do we fill out the cell here? Oh. Can I use this? Good. So this is going to represent, good. So this is going to represent 1 operand, okay? And then these other 3 would represent the next operand. Let me use this color, all right? So, and then this 2 bits would represent the opcode, right? So if you remember, if we're going to use 2 bits to represent the opcode, how many possibilities, how many possible instructions can you represent using 2 bits? Remember, if you have 2 bits, you can have 0, 0, 0, 1, 1, 0, 1, 1, right? So this is, you have 2 raised to the power, where's my raised to the power on this machine? So 2, I can't really find my keys, folks. 2 raised, okay, there you go. Raised to the power 2, which is equal to 4. You have 4 possible instructions. If you use an 8-bit architecture and you reserve 6 bits for opcodes, where each opcode, 6 bits for the operands, where each operand is consuming 3 bits each, you can have possible 4 instructions that can be represented. If 0, 0 is an instruction, 0, 1 represents an instruction, and so on and so forth. Okay, so if you go back to the question, what it asking? 3 instructions with 2-bit operands. Okay, it looks like we can do that because, again, based on what we just computed here, we can have 4 instructions, so we're good. So what about 2 instructions with 1-bit operand? So let's do the same thing. So I'm gonna copy this table. I'm gonna put it down here, and it says 2 instructions with 1 4-bit operand. Okay, 2 instructions with 1 4-bit operand. So a 4-bit operand means that all of these will be, let's see, will be our operand. So I'm going to change all of this, and all of this one here, I'm going to take this 1 4-bit operand. 1 4-bit operand. I'm going to take all of this out. I'm going to remove the, I'm going to remove this. And then what's the next one? 4 instructions with 1 3-bit operand. So what does it say? It says we need 3 times 23, which is equal to 192 bits for the 3-bit operands. 2 times 24 for the 4-bit operands. And 4 times 23 for the 32-bit operands, resulting in 256 bits. And then they go ahead and say that with a total of 256 bits, we can exactly encode our instruction set, which means that we can do it. Now, how did we get the 3 times 23? 3 is the number of instructions. 23, 3 times 23. Let me see here. How did we get this 23 again? I was reading through this, and let me just see. Just give me a second here, folks. Let's talk about this. Let's figure this out here. What page is this on? In the textbook here. Opcode, operands. Opcode and operand. Where is this happening here? Number of operands and instruction length. So page 305. We talked about postfix. We talked about simplification, expanding opcodes. Then we talked about to show that there are enough bits, we need to calculate the number of bit patterns. This is example. How do we know if the instruction set we want is possible? Let's see. So students, let me do this just to save us time. Let me record a video on this one. Let me record a video to explain this a little bit more in detail, because I was headed down one path to explain this, but it doesn't seem to be consistent with what I am reading here from a textbook. So I'll send you guys a video. The question is, how are we getting this 23 bits, right? How are we getting 23? We have 3 instructions. So obviously an instruction is a combination of the opcode and the operand. We have 3 of those. We want to have 3 instructions. So we want to be able to represent 3 instructions that have 3-bit operands, which is this picture which I kind of demonstrated here. Each of these things is 8 bits. 8 times 3 is 24, right? If we want to represent 3 of these kinds of things, right? So 8 times 3 is 24. So I'm trying to understand where this 23 is coming from. So I'm going to have to record a video and get back to you folks, because again, I need some clarity on myself on what this is all about. Okay, so I promise you all a video to clarify this particular concept. Okay? All right, so let's keep on this real quick. Let's keep moving. I'll come back to these ones. These are instruction sets, 3 instructions with 2-bit operands. This is what we're talking about here. This is instruction 1, instruction 2, instruction 3. Excuse me, this is a 2-bit operands. Then they talked about this escape opcode. I wonder if this is what is tripping us, but I'll record a video and get back to you folks on this one. And then this is the same kind of instruction set, 2 instructions with 1 4-bit operand, which is this one. But then now we have 2 escape codes. Again, I gotta understand this. And then this one. So let me record a video dedicated to this for this particular one. I think this is covered in your textbook on pages 313. I'm gonna have to dive into this and get back to you folks on this one. All right. Okay. So the next slide deck. Instruction types. You know, I think we saw some of this in the American Computer, right? There's different type of instructions. You have moving data instructions, arithmetic instructions, Boolean instructions, bit manipulation instructions, I/O. You know, so this is what this is all about. These are the various type of instructions that you have captured in the instruction set architecture. Okay. Addressing modes specify where an operand is located. Remember, the operand is the data. Okay, the operand is the data, so the computer has to know where to go find the data. You can specify a constant in the register. No, you can specify a constant, a register, or a memory location. So if we go back to our diagram here, if this was, let's say, if an 8-bit architecture, with 4-bit operand, okay, and the other 4 bits are reserved for, these other 4 bits are reserved for the instruction. The operand, which is, I'm going to make this color, let's see, green, okay, so I'm going to make this one green too for the opcode. Okay, so if this is the operand, okay, this is where the data is going to be stored. So memory addressing mode tells the computer how to interpret the data that is stored here. If let's say that the number here was 1, let's say 0, 1, 2, and 3, the computer would interpret these numbers based on the addressing mode that comes with the instruction set architecture. Okay, so you see constant means that, constant literally means that what the computer sees is what it is. Register means that that number that you see here is a register address. Memory location means that this number that you see is a memory location, and so on and so forth. Okay, so that's kind of the addressing modes that the computer uses to determine how to retrieve the data. Okay, so that's what this is all about. Now let's see here. The actual location of an operand is its effective address. So remember how the computer takes this and translates this to where the data is. That location of where the data is the effective address of the operand. Okay. So now it goes on and says that certain addressing modes allow us to determine the address of an operand dynamically. And a lot of computers these days, allow for this dynamic addressing because it gives you the flexibility. And for dynamic addressing, there's several ways. There's several kind of methods. Immediate addressing means that the data is part of the instruction, right? So if you imagine an instruction set like this, if you see an address like this, it means that this is the data. Okay, and this is covered on pages, you start getting coverage here on page 319. Okay, page 319. Right, so you see immediate addressing is where the data is part of the instruction. So in this case, this is the data. 0, 1, 2, 3, 4 is the data. Let's say this was M U L T, the instruction. Right, this is the data. Okay. Direct addressing is where the address of the data is given in the instruction. So in direct addressing, this is the address of the data. So this is not the data. This is the address of the data. In register addressing, this is the address of the register. Okay, in direct addressing, this is the address. This is where the address of the data is given. In what's the next one here? In indirect addressing, it gives the address of the address. So this is the address of the data. Indirect addressing. So this is not the address of the data, but the address of the data. And then register indirect uses a register to store the address. Okay. So this is going to be an address of a register. We go to that register and we find the address of the data. Okay, so read through this pages 320 to 321 would give you some examples on this addressing modes. Okay, and if you have an example, any questions again, please feel free to reach out to me. Okay, let's see what is here. Addressing, we talked about this. Now there's index addressing, some other types of addressing where we're using an offset, which is added to the address in the operand. So in index addressing, there's going to be an address in the operand, and then we use an index to specify the actual address of the operand. Base addressing is similar. So read through this and you would notice that there's always trade-offs, right? When you do an addressing scheme, there's always trade-offs. So you'd read in later chapters that embedded systems typically would use one of it's either index or base addressing because it's simpler to execute, and it uses less instructions. Okay. So we can skip through this. Again, these ones are covered in pages 320. So just read through that, and if you have any questions, please let me know. All right. We're going to the next section of the textbook, which is called pipelining. I may have to record another video to illustrate this concept, but pipelining. But in I think chapter 4, you guys learned of the fetch, decode, and execute cycle of a CPU, right? Before a CPU has to execute instructions, like if this is an instruction, it has to fetch it, it has to decode it, and it has to execute it. So that's the fetch, decode, execute. And this lines up with those CPU cycles, right? I think if you guys did some further reading, you have the clock cycles, and for every clock cycle, there's something that's happening on the machine, right? So what pipelining is a mechanism that allows machines or CPUs to execute numerous instructions at the same time. Okay, so this is covered thoroughly in chapters 2, 323, right? So a machine should not just be executing one instruction. Machines should be executing multiple instructions. That's why you hear of parallelism, where a machine can execute multiple instructions at the same time. So the number of instructions that the machine can execute at the same time is what they call the number of pipelines, right? Number of pipelines. Now, and each pipeline has a stage, And for each stage, something happens, right? For each stage in the pipeline, you're either doing a fetch, you're doing a decode, you're doing an execution. Those are the various stages of the pipeline, right? So read pages 323 of your textbook, and there's some good examples. There's some math here that talks about speed up, but don't worry too much about that right now. Just understand the concept of pipelines, because this ties into parallelism, right? You read about the Intel Pentium 3, the Intel Pentium 4. The difference between the Intel Pentium 5 and 3, for example, is the number of stages, of number of pipelines that the Intel Pentium 5 has compared to the Intel Pentium 3. Okay, so it's important for you to understand not necessarily the mathematics that you see on 324, but the whole concept of pipelines and how the number of pipelines increases the parallelism of a computer. And of course, like I said, anything that's trade-offs, the more pipelines you have, the more resource contention you could have, and then we're going to have additional logic to ensure that we don't have this resource contention. Okay, so read through that again. This is, for example, in this particular case, right? S1 here is the fetch instruction, S2 is the decode instruction, S3 is the calculate, right? So this is one pipeline, one instruction being executed is another one, and the number of parallel instructions that can be executed at the same time is the number of pipelines. Okay, so read through that again. There's some mathematics here. This is not very important. Read through this just to kind of wrap your head around some performance. But again, the key concept that you want to grasp is the whole concept of pipelines. Okay. So I will skip through this. This one just talks about some of the issues that you may have when you have a lot of pipelines. So I'm not going to just go through this. I'll skip through this. And the end of this chapter talks about real-world examples of instructions or architectures. It talks about the Intel, the difference between the Intels and the MIPS, read through this. Again, something I don't really need to explain. I think Intel is based on, Intel uses little endian, yes, with variable length instructions. Okay, so what they're saying is that in Intel, an instruction could be 8 bits, 16 bits, 32 bits, right? It's not fixed. Okay, but little endian. So little endian means that the least significant byte is represented in this type of registers. Okay, so the MIPS uses little endian as well. Word addressable 3. It says word addressable 3 address fixed length instruction set architecture. So the MIPS, the instructions are fixed sets. So fixed number of bits are used to represent the instructions. Again, there's always trade-offs, right? There's always trade-offs when you do fixed set instructions versus variable set instructions. So these architectures are covered on 328, 329. Read through that real briefly. It should be a good reading for you folks. And towards the end of the chapter, it talks about a Java virtual machine. I think that's an interesting one. A lot of you must have had programming experiences in Java. Read through this. Java, it talks about, how the Java virtual machine is it does not necessarily create machine instructions. It creates what we call bytecode. Now, Java and C# are kind of the same kind of thing, right? It creates bytecode. Bytecode is not really a machine instruction. There's still something that needs to take that bytecode and translate that to actual machine instruction, right? So that's why you have a JVM for Windows, a JVM for Linux, a JVM for mainframes, because when you compile your Java program, it does not create machine instructions. It creates opcode, and this is shown on pages. Page 336 of the textbook, and that opcode is now translated by the Java virtual machine to actual machine code. Okay, so read through that, and that's what the slide deck is saying. Bytecode, C# is the same thing. read through that, and if you have any questions, please reach out to me. Okay, so in this one, it's saying that when you write your code in Java and you use the Java compiler, when you look at the result of the compiler, right, what you think is bytecode. It's not actually an Intel or a MISP. What is it, MIP? Excuse me, MIP. I can barely talk. It's neither an Intel nor a RISC, whatever, right, instruction set, because the Java virtual machine on those operating systems have to take the bytecode and translate that to actual instructions that can be executed by the CPU. All right. So the Java bytecode is stack based. We talked about stack and things that just popped in and out of the stack. It says it has 4 registers that provide access to 5 regions in main memory. Interesting. And it uses the offset-based addressing scheme. Okay, so Java was designed for platform interoperability, not performance. So on page 324, you see that there's a difference between Java and C++, right? When you compile a Java program, you're creating bytecode. What the Java virtual machine does is it takes the bytecode and it translates that, it converts that to machine code. That's why it allows you to be able to, that's what allows a Java program to be able to be executed on different operating systems. C# is the same today, right? You have a C#, I think the .NET CLR for Windows. You also have the .NET CLR for Linux today. Okay, so same kind of thing. Now, if you write a C++ program, though, and you compile that, that is compiled against the operating system on which you compiled that C++. When you write a C++ program and you compile it on a machine, the binary that's resulting from that compilation is specific to that CPU architecture on which the code was compiled. So if you write a C++ program on your MacBook and you compile it on your MacBook, you cannot take that binary and go run it on Windows, right? Because the code was compiled against the CPU architecture that the compiler ran on. Okay, so that's the difference between Java, which is not a compiled language. This Java virtual machine type languages, Java, C#, and compiled languages like C, C++, COBOL, ADA, and stuff like that. These ones are optimized for performance. Okay. Then you have on the other side interpreted languages like Perl, Lisp, PHP, right? These ones are actually interpreted. So as they are executing, you have compilation occurring on the fly. Okay, so very different from Java, where you already have something that's compiled. The Java virtual machine has to compile, do an additional compilation. But with interpreted languages, the source must be interpreted each time the program is run. Okay, so something for you to pay attention to. So read through the remaining real-world examples. Again, very straightforward reading and interesting reading, especially given that a lot of this stuff is relevant today. And if you have any questions, please feel free to reach out to me. Feel free to research other YouTube videos that would help. I would find some helpful videos and I'll send them to you. And I promise that I would put together a video to further explain this concept of extending opcodes, where I was not able to wrap my head around it, given that it's already 10 o'clock here. But I will come up with a video that talks about just this concept. If not, I would find a video on YouTube that talks about this exact concept, and I'll share with you folks. And again, reach out to me if you have any questions. Okay, so I hope this was helpful. Again, this is not really meant to replace an in-person class, but just to kind of guide you through the section, how you want to study through the section, some areas that you should pay attention to, those areas that you can just breeze through, and those areas that I think interesting reading. Okay, and again, we will talk to you folks next week. Thank you.